Okay, so we're going to move on to power series now. Power series, basically we leave numerical series behind except for a few applications, and that'll make sense when we actually arrive at it. Um, but basically, whereas we were given geometric series that were something like, a sub 1 times r to the n minus 1, and we knew that that meant something like, a sub 1 times r to the 0 plus a sub 2 times r to the first plus, a sub 3 times r squared plus dot 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 plus, a sub a sub, n times r to the n minus 1 and off to infinity, right? And so we have, specific instances of that, like, let's say we have 2, and then we want, 2/3 to the n minus 1. And so it's, 2 plus 4/3 plus, 8/9 plus dot, 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 all the way out. And there was a formula that we had, and we knew, because I showed it to you last year in 2 separate iterations, that this was equal to that. Okay? Well, what happens when we move from numerical series to power series, and this isn't the only instance of this, but this is a nice sort of segue into it. Let's say instead of something like this, what we have is, or let's just go ahead and put n is equal to 1, and let's say our first term is 1, but instead of r, let's put x. Well, that winds up being 1 plus x squared plus x cubed plus all the way out. Well, that should then be equal to 1 over 1 minus x should be equal to this, right? Based upon this relationship right here, all I've done is replace a sub 1 with 1 and r with x. So this should work, right? This should be representative of this. Now, remember that this relationship right here is only for when the absolute value of r is less than 1, which is a nice way of saying, between -1 and 1. Okay? So this is only true, and since we replaced r with x, this is only true between -1 and 1 for x. So this infinite polynomial, for lack of a better way to describe it, it's not officially, but basically that's what it is. This infinite polynomial will mimic the behavior of 1 over 1 minus x perfectly as long as x is between -1 and 1. This is what is called an interval of convergence. Okay? It converges, meaning this mimics this perfectly on this interval. Okay? Outside of that interval, you're not going to get a perfect match. You're not going to get this infinite polynomial matching point for point onto this right here. Okay? So basically what happens is we have power series, and of course this is just one example of them. We have power series, which are infinite polynomials, and those power series mimic the shape, the contours of a particular function over a particular interval. And that interval can be a point, it can be a finite interval, or it can be an infinite interval. Okay? This one is obviously finite. It occurs between -1 and 1. Only the points in between, not at the endpoints, and certainly not beyond that interval. Okay? So let's go ahead and let's actually do another example and show you that this sort of gets beyond that one particular sort of geometric series segue. Let's say we have n is equal to 0 to infinity of x minus 2 to the n over 10 to the n. Now, you can actually sort of expand this out, right? This basically can be expanded out, and it winds up, you plug in n is equal to 0, and you end up getting 1, right? You plug in n is equal to 1, because, this actually, since the n's are the same, this actually can wind up being that, right? So n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Now, what we want to know is, okay, if this is a power series, this is the sigma representation of a power series, where does it converge for the function that it represents? Okay, basically, if I want to use the power series in order to get values for this function, what interval am I dealing with? Can I use the power series for any value, or do I have to use it for specific values? Well, here is where the ratio test is actually going to come in handy. And now remember that when I'm dealing with the ratio test, it's all about whether that ratio, okay, it's the relationship of the ratio to 1, okay? Let me go ahead and pull this up. The ratio test is here, right? If I have sigma from n is equal to 1 to infinity of a sub n, if I take the ratio and a sub n plus 1 over a sub n, and it's less than 1, okay, then it converges, okay? If it's greater than 1, it diverges, and if it's equal to 1, then it's inconclusive. But what we're going to do is we're going to take that and we're going to sort of bend it to our purposes, okay? Now we know that we have x minus 2 to the n plus 1 over 10 to the n plus 1 times 10 to the n over x minus 2 to the n, okay? So let's go ahead and plug that in, okay? Let's go ahead and simplify that. So we have the limit as n approaches infinity. Now remember, what happens here is all of these cancel with all but one of these. All of these cancel with all but one of these. And what I'm left with when I have x minus 2 over 10, notice that there's no n involved in there anymore. So the limit is just x minus 2 over 10. Well, when will that converge? Well, just like the normal numerical ratio test, it will converge when it's less than 1. Okay, or when the absolute value, because this actually should be that. So what happens here is we can turn into a 3-part inequality. Now, here's the thing. I've already discussed what's called the interval of convergence, okay? What I want to know also is what is the radius of convergence, and that is this number right here. How far either way from the center of the interval do we have to go in order to have that interval of convergence? Okay, so all intervals, if they are finite, will have not only a radius but an interval in itself, okay? So the radius here is 10 because the center is obviously x is equal to 2. The center is x is equal to 2, and if I add 2 to both sides, it winds up being that, okay? So we know that this right here, okay, is what is called the radius of convergence. Now, is this the interval of convergence? Well, it's not really that simple, okay? We have determined the interval right here. What is still a question, however, are the endpoints. So that's where the numerical series actually still factor in, okay? So what I'm going to do is I'm going to figure out 2 numerical series, taking -8 and plugging it in for x, and then taking 12 and plugging it in for x, and deciding what happens at those two numerical series and whether they converge or diverge. So let's go ahead and plug in -8. So I get -8 minus 2 to the n over 10. And I'm going to get 12 minus 2 to the n over 10 to the n. Okay. Well, this just winds up being -10 to the n over 10 to the n, or it winds up being n is equal to 0 to infinity of -1 to the n. That's divergent, okay? It's an alternating series, and it doesn't do anything but flip-flop back and forth between 1 and -1, okay? This right here winds up being 10 to the n over 10 to the n, so it winds up being just 1 to the n, and that diverges as well. Okay, so both of the endpoints diverge. So this actually did wind up being my interval of convergence. And you can, -8 to 12, interval notation or whatever. This right here is my interval of convergence. So what we need to do is when we are presented with a power series, we need to apply the ratio rule. And we need to basically figure out, based upon this relationship right here, what our radius is. We get down here to sort of a first sort of rudimentary interval, and then in order to finalize our answer for the actual interval of convergence, I need to test both of the endpoints by plugging both of those endpoints back into the original power series for x and checking the numerical series that they give us, okay? And then once I've gotten the radius and interval of convergence, that's usually all it's really asked for in one of these questions, okay? Let's do one more example really quickly, and then we'll have a second video where we just run through example after example after example after example. It's obviously always the first one that's a little bit difficult, because I'm actually, explaining the concept as we go through. Once we've gotten the concept down, the rest of these should go rather simply. Okay. What is the interval and radius of convergence for this power series? Well, obviously, we're going to stumble upon the radius first. But, we need to get a sub n plus 1, which is going to be n plus 1 to the x to the n plus 1, all of that over n plus 3, right? So I have the limit as n approaches infinity of n plus 1, x to the n plus 1 over n plus 3 times n plus 2. And of course I would be dividing by this original a sub n, but to divide by it is to multiply by its reciprocal. Okay, sorry, that's just supposed to be a sub n. Now I just need to do some simplification by canceling. All of these cancel with all but one of those. And what I have here is I have the limit as n approaches infinity of n plus 1, n plus 2, n plus 3 times n times x. Well, what happens to this ratio as n goes to infinity? Well, it's the whole comparing the leading coefficients. That is going to go to 1, okay? So the limit as x approaches infinity, as n approaches infinity, winds up being x. And in order to find out where that converges, our sort of whatever the expression is that the limit spits out, the absolute value of that has to be less than 1. Now, this doesn't take a genius to figure out that our radius of convergence is 1. Okay? Radius of convergence is equal to 1. Okay? Now, what that means also is that I have, a preliminary answer on our interval of convergence, but what must happen now is I must test -1 and 1 by plugging them back in to determine whether whether the endpoints converge or diverge. Okay. So we have -1 to the n over n plus 2. And then we're going to go ahead and plug in, and if I sort of do that, you can actually see the original. All I'm doing is taking that endpoint and plugging it in for x, taking that endpoint and plugging it in for x. Okay. Now, what happens here is this one winds up being an alternating series. Okay. So we have -1 to the n, and n over n plus 2. Now, does this go to 0? Remember the alternating series test. That does not go to 0. That goes to 1. So basically what I'm going to be doing as n goes off to infinity is I'm going to alternatingly be adding 1 and subtracting 1 and adding 1 and subtracting 1, or numbers that become increasingly close to 1 and -1, right? As this becomes increasingly close to 1. That describes a divergent series. That does not pass the alternating series test. And neither does this, okay? This, even without alternating, this is not going to 0. Each successive term is not getting smaller and smaller and smaller and smaller and smaller. It's actually getting bigger and bigger and bigger and bigger and bigger. I mean, very, very modestly so. But you got to plug in 1, and we're going to get what? 1/3. We'll plug in 2, and we're going to get 2/4, or 1/2. Plug in 3, 3/5. Plug in 4, 4/6, or 2/3, okay? Plug in a million over a million 2. So this is actually increasing. So this describes a divergent numerical series as well. This is indeed our interval of convergence. Okay? So whatever function this represents, okay, it has a radius of convergence about its center. Its center is 0. And its interval is -1 to 1, non-inclusive on both endpoints. All right? Now, we're probably going to do one more video on this. This is really, except for just introducing just the general notion of a power series and basically running through examples of interval and radius of convergence, there really isn't much going on in 11.8. In 11.9 and 11.10, we might have more than 2 videos per section, simply because those sections are a little bit more robust, there's a little bit more going on, and therefore we're going to have to discuss more than just this one thing, okay? But be on the lookout for video number 2 for 11.8, and then we'll move on to the last couple of sections of the chapter. As always, please do email me with any questions that you have. Bye.